Okay, continuing on for Chapter 8. This image is from page 184 in your textbook, and it looks like a Japanese flag, but it's not. Basically, this is a trick you can do to trick your eyes, to trick your perceptual system into thinking there's movement. So you stare at this dot for light it up really well and stare at it for 60 seconds. Just stare at it to burn the image into a spot on your retina. Then go into a dark room, and what you'll see is the dot, and it'll appear to be floating and moving. And the reason for that is because what you're doing is there's eye movement, right? There's eye movement, but there is a fixed object that is not moving on your retina. So what's happening there is that a CDS, corollary discharge signal, is being sent to the comparator, but not the IDS. So as a result, since you've only got one of the signals going to the comparator, because the retina image is not moving, but the eye is moving, you end up with an illusion of movement. And this is what happens basically. So so your eyes are moving, so you're getting the muscle signal. So the muscle movement is being there's a signal that is moving your muscle, and of course these muscles here, and of course that signal branches off to the corollary discharge signal. However, there's not an IDS signal being sent because there's no movement being detected on the retina, because the little dot that you were looking at is stuck right there where you burned it, bleached it into your retina. As a result, since the eye is moving but the image is maintaining itself on the retina, your brain thinks that your eye is tracking something that's moving. Because your eye is moving and the retinal image is not moving. So as a result, it makes it look, it gives it the illusion of movement. There's some physiological evidence for this corollary discharge theory. So for example, if you get damage to the MST, the medial superior temporal area of the parietal lobe, there is you do get disruptions in the ability to perceive movement. So basically, whenever somebody with this type of brain damage is looking at something that isn't moving, it'll look like it is moving when you move your eyes. There's also neurons that have been located in monkey brains that only respond when a stimulus moves. All right, so they do not respond when the eyes move. So in other words, when the retina is being presented with a changing landscape, they only respond when a particular object that is being focused on in the optic array is moving. So there is some evidence for at least some components of the corollary discharge theory. So, and here's an example. Of course, the higher these little bars go, the more firing there is. So this is on the y-axis we have strength of the neuron firing, and on the x-axis we have time. So basically what's happening is the bar is moving, so they are able to move this bar back and forth, and whenever the bar does move, for example, if the monkey's looking here and the bar all of a sudden moves from B to this position here, there will be a firing. The bar moves across this square. If, however, the monkey is fixating on this and the whole landscape moves, so the fixed point moves and this moves as well, there is no movement. I mean, there is no firing. So, as in other words, the monkey's eyes are sweeping across. This is what happens when the monkey's eyes are sweeping across, looking from right to left and left to right. There's no movement. I'm sorry. There's no signal being generated, which gives us some support for this corollary discharge theory. Okay, so a number of the responses of the neurons in the visual cortex are pooled together, and they're pooled together probably in the medial temporal cortex. All of the output of the V1 neurons in the visual cortex and the primary visual cortex make their way to the medial temporal cortex. Now remember, the medial temporal cortex is part of the where action stream. So where having to do where things are located in space and what can you do with them. All right. So essentially, or what is being done, I should say, for action. So essentially what's happening here is that the output from the V1 neurons is going to a place where the brain can tell, or the brain can further analyze where things are going in space and time. And we have seen evidence for this in the medial temporal cortex of monkeys. There are also neurons in the striate cortex that respond to the movements of ends of objects. So, for example, the end of a bar, right? If the bar is moving, if the end of the bar is moving, then the neurons will respond. So we do have there seem to be a lot of different areas for interpreting only movement of objects in our brains. We still don't know how it all comes together to form a coherent perception, but we're starting to understand some of the physiology. So Newsom et al. Did some experiments with what he called coherence, and looking at the behavior of these medial temporal neurons. Now, the hypothesis was that the more coherent movement that you can see, the more of a movement pattern that you can see, the more the medial temporal neurons will fire. All right, so basically what he did was, let me show you the coherence experiments. Now, essentially what they did was they showed monkeys these moving images of these dots. So these dots would appear for just a few milliseconds, move real quick, and then disappear to be replaced by another dot. That's what is indicated here by the dot and then the arrow. So dot, arrow, dot, arrow, dot, arrow. And these dots would move in the direction of the arrows that you see on this diagram. And essentially what he did was he adjusted what he called the coherence. This is one of the independent variables that he used, coherence. This image here represents what the monkey would see if coherence was 0. In other words, all of the dots are just randomly going in a pattern. So there's really no particular movement pattern, no coherent movement pattern to detect here. It's just a bunch of random dots appearing and disappearing. On the other hand, if you look over here on the right-hand side, you see 100% coherence. In other words, 100% of the dots that appear are all moving in the same direction. And then you have the half and half, 50-50. So half the dots are moving in the same direction, and the other half of the dots are just random. Okay, and then of course you can adjust this. You can have 25% coherence, or 75% coherence, or 20% coherence, and the higher the coherence, the more of the dots are going together in a group in one direction. So it's obviously easier to detect motion here in the 100% coherence group. You can clearly see that there's some sort of motion in a particular direction. Here it's a little bit harder, but you can still detect it. And here, of course, it's impossible because there is no movement. So going back to the study, what he did was he did the coherence to vary the dot patterns, and the monkeys were taught to judge the direction of the dot movement. So the monkeys were trained to move a joystick or push a button in the direction of the movement of the dot. So the monkeys could tell the experimenter what direction the dots are moving, and the neurons in the medial temporal lobe were measured. When you did this, basically, the more coherence you got, the more the firing of the medial temporal neurons, and the better the accuracy was. So this was a very clear relationship between our ability to detect motion in our environment, or the monkey's environment, and the firing of these neurons. Notice that in this experiment, all of the monkeys saw dots moving around, but it was only those monkeys that were perceiving coherent movement of dots where the medial temporal neurons fired. So what happens if we lesion this part of the brain? In other words, if we drop a chemical or an electrical burn into that part of the brain? Well, a normal monkey with a normal brain can detect motion with only 1 or 2% coherence, if you can believe that. So if only 1 or 2% of the dots that appear on the screen are moving in a particular direction, a normal monkey can detect that, which is pretty amazing. But a monkey with a lesion in the medial temporal cortex can't detect any motion until the coherence hits 10 to 20%. So you get almost a factor of 10 decrease in the monkey's ability to detect movement in this experiment when you lesion the medial temporal cortex, which gives us further evidence that this part of the brain is really important in detecting movement, or in helping us to detect movement. So we have this relationship here. We have this very interesting relationship here. The perceptual cycle. Now, we talked about this in Chapter 1. You have this relationship between stimuli, which is what we're perceiving in the environment, and when the dots are in this particular coherence experiment, when the dots are moving in the same direction, we perceive movement in that direction. So the stimuli leads to a particular perception. The stimuli also activates the physiology in very specific ways. So the stimuli activates cortical neurons, and the firing of those cortical neurons in the medial temporal area and the perception of the dots are related. So we have this relationship, this correlation essentially between the stimuli, the physiology, and what we're perceiving. You can also further studies in lesioning and stimulating this part of the brain, the medial temporal cortex, were done by Movshan and Newsom. So monkeys were trained to indicate the direction of fields of the moving dots in varying coherence, of course. And of course, from that experiment, we know that neurons in the medial temporal cortex that respond to a specific direction were activated. So what they did was, while the monkeys were judging the direction of the way the dots were flowing, they stimulated the specific neurons that lit up or that were activated with only a specific direction. And what happened there was the monkey's perception changed. The monkey would then say, oh, the dots are going in that direction, in the direction of the direction that is linked to the stimulation area of the brain. So if they stimulated, for example, if they stimulated a part of the neurons that were activated when the dots were flowing in this direction, they would stimulate those, and let's say the dots were really flowing in this direction. Well, when they stimulated the neurons that are activated when the dots flow in that direction, even if the dots are flowing in this direction, the monkey would say, no, they are flowing in the direction that the brain is being stimulated. Again, giving us some really solid evidence that the medial temporal area is critically involved in helping us to perceive motion. So again, with no stimulation, the monkey's going to say, oh, see dots going that way, they're going that way. But if I stimulate, if the dots are going that way, but I tell them I stimulate the neurons that tell the monkey that the dots are going downwards, the monkey's going to report to me with its behavior that it's perceiving this. It's perceiving whatever part of the brain is being stimulated.